In activity 5.5, we're going to use our graphing calculator to help us explore the relationship between little f of t, which is t over 1 plus t squared, and capital F of x, which is the integral from 0 to x of little f of t dt. First thing we're asked to do is plot from negative 10 to 10. So here's the plot of our graph in a standard window. What we might do to see a little bit more of what's going on with the function is we might change our y min and max so we can see a little bit more what's going on with the function here. So if you look, it goes at about negative 1, it goes to negative 1/2, and at about positive 1, it goes to positive 1/2. So my scale, can't quite see it there, I'm going to do negative 1 and negative 1/2, and here I'm going to do 1/2 and 1. And so I'm going from negative 10 to 10. And like we said, that looks like it's got the max right about here and the min right about here, and it goes through 0, 0, and it's asymptotic. So drawing our graph might look something, oops, like this. All right. Gives us an idea of what the graph of little f of t looks like. Now, as far as the relationship between these two, what we know from the second fundamental theorem of calculus is that capital F prime of x is equal to little f of x. So this is the derivative of this function. So now we can actually use our derivative test to figure out where this function is increasing and decreasing. So we can make our number line, but notice what we see. The derivative is negative on the left side of the axis and positive on the right side of the axis. So we would expect capital F of x to be increasing from negative infinity to 0. Sorry, decreasing from negative infinity to 0, and increasing from 0 to infinity. So we can tell that just based on our graph, right? We have a 0 at 0, and so notice what's going to happen. It's going to go decreasing to increasing, so we expect this function to have a min at 0. Now, we're also going to go ahead and use a second derivative test, given that the derivative of f, in other words, little f prime of t, is equal to 1 minus t squared over 1 plus t squared squared. So we're going to do a second derivative test on here. And I'm just going to write it up here, and then we'll put our notes there. So I put in a number line, and now f prime has zeros at negative 1 and positive 1. And now we're going to test points. Well, the denominator is always going to be positive because of the square. So if we do a test point of, say, 0, notice if I plug 0 in for t, the numerator comes out positive. That means capital F will be concave up between negative 1 and 1. Over here, if we use a test point, negative 2, say, we can see that this numerator will be negative. A negative over a positive is a negative. F will be concave down. Similarly, if we were to use positive 2, we'd see that this is negative, also concave down. So for our function, it's going to be concave up on the interval negative 1 to 1, and concave down on the interval negative infinity to negative 1 and 1 to infinity. So we'll get a good look at, we already have a pretty good idea of what's going on with this function capital F of x. Now, the next thing we're asked to do is use technology appropriately, to calculate a couple of values. I'm going to use the graphing calculator to do this as opposed to Riemann sums, just to show how we can do an example where we do that. So if I wanted to calculate f of 5, what that is that's the integral from 0 to 5 of f of t dt. And so what I'm going to do, I already have it entered in as a graph in my calculator because we saw the graph here. I'm going to do second calculate. I'm going to pick option number 7 here, and my lower limit is 0, my upper limit is 5, and I get my definite integral is 1 point. I'm just going to round to 2 decimal points for time's sake. F of 10 we can do very similarly. 0 to 10, and I recommend you try this. This is a great way to check your answers. We're still going to do these algebraically, but I think it's important that we have a way of using our technology appropriately. So 0 to 10, and it's 2.30, or 2.31, excuse me. Now, those are the only ones I'm going to calculate in this video because I think that's enough instruction on how to do it. It's very quick. Something interesting about this function capital F, if you start using the negative limits, for instance, if you did 0 to negative 5, what you would find out is you would actually get the same answer. Same thing with negative 10. And so we can keep calculating values this way. What we're going to have is an even function. So if we calculate, for instance, f of 1, well, it's going to be the same as it is for f of negative 1, and using the calculator, that came out to be 0.35. We can do this again with, say, f of 2. It's also f of negative 2, and that comes out to be 0.8. So we can see that increasing nature in the positives and a decreasing nature in the negatives. Also, we know that f of 0 equals 0 because that's the place where the limits would be equal to each other. So we know it goes through 0, 0. And if we wanted to go from negative 10 to 10, and perhaps, we know that at 10 it goes up to 2.3, so let's set our scale to a maximum of 3. And so if we do this, then perhaps there's 1, there's 2, so there's our point here. We can start to plot a few of these. We're going to see the same point here. So that nice symmetry is going to make this a little bit easier. At 5, we're at about negative 1.6, or sorry, positive 1.6. Same thing at negative 5. And now we're going to see it start going down. Let's just plot one more point, f of 1, for instance, at 0.35. Just going to be down here somewhere. And we'll have another point here. So we can see that concave down nature until we get to negative 1. Then it's going to come through here and go concave up a little to positive 1 and be concave down the rest of the way. So there's our graph of y equals capital F of x. Now, we're going to learn shortly how to find the antiderivative of this function analytically, but I've already done that, and so let's go ahead and take a look at the graph, and we need to establish the same window to see how we did. So we can already see that little V shape in there. That looks pretty good. We did a y min of negative 3, which doesn't matter too much, but for symmetry's sake we'll put it in there. And we see with just a few points and knowing about the concavity and increasing, decreasing behavior of the function, we actually drew a pretty good representation of the graph.